say about that. Let's talk about the next thing. So we last time we finished talking about the L'Hopital rule, and this time, so that's actually the end of that chapter in the book. I think chapter 6 was generally about inverses of things and also L'Hopital's rule for some reason. And then chapter 7 in the book is about a bunch of different integration tricks. So we are going to talk about integral tricks for the next little while here. Really, as far as integral tricks goes, the only one that we've talked about so far is the U substitution. And the second kind of classic integral trick is the integration by parts. So that's what we're going to talk about today. You may be familiar. In my opinion, the integration by parts, I think, is actually a little easier than U substitutions. U substitutions can be difficult from time to time. Integration by parts is to me, a little more straightforward. Although it has a formula that you have to remember. I mean, it's not a very complicated formula, but provided that you remember the formula, it's to me, it's a little more straightforward than doing the U substitution. Anyway, the integration by parts is another integration trick, and this one, the U substitution, is based on the chain rule. It's all about like the dx versus the du, and these come from the idea underlying the whole thing is a chain rule. The integration by parts is based on the product rule. So I will write, just to refresh our memory, the product rule. I'm going to write it in kind of a weird way. Rather than, usually you would write derivative of like f times g when you write out a formula for the product rule, but I'm going to call them u and v here just because we're thinking of this in terms of things inside the integral sign. And also I'm going to use just d rather than writing the derivative thing. This is going to look a little weird, but if I were to write the product rule in this way, so d means derivative, and u and v are two things being multiplied together. That's a multiplication inside. Anyway, if I were writing the product rule, it would say u dv, that's the first thing, u, times the derivative of the second thing, that's dv, plus the second thing, v, times the derivative of the first thing, that's du. So this is the product rule written in a slightly strange way. All right. And now from here, we are going to just take the integral of everything on both sides. If we integrate everywhere, the left side says integral of d of uv, and the right side says integral u dv plus integral v du. This is basically the integration by parts formula. On the left side, we can simplify. What is integral of derivative of uv? It's the integral cancels the derivative, right? This is the antiderivative and the derivative have no effect. So this is just uv, is integral u dv minus plus integral v du. And this is basically the integration by parts formula. We usually don't write it this way. Usually we solve for integral u dv just by subtracting integral v du onto the other side. So just rearrange this a little bit. It says integral u dv equals uv minus integral v du. And this is the formula that you should memorize. This is the integration by parts formula. It's not all that complicated. It comes from the product rule. It's basically a rearranged version of the product rule with integral signs in there, all right? And when we use this, you choose for yourself which parts of the integral are the u and the v, right? So in that sense, it's kind of like a u substitution where, like, when you see the integral, you have to decide for yourself what to make the u in the u substitution. In the integration by parts, you have to look at the integral and decide for yourself. Actually, there are two main parts. If you think of looking on the left side, you typically are going to be presented with an integral like this, and your job will be to choose part of this is going to be the u, and the other part of this is going to be the dv, and then you do a bunch of stuff and rearrange it into this. Hopefully this integral, after you do the formula, you end up with another integral, which you still have to do, but hopefully if you've done things properly, this integral is easy to do, and then you can finish with one more step. So let's do a very simple example, and this is like everybody's first example integration by parts formula. All-time classic. X times e to the x, all right? I'm going to look at that, and your job is to, well, first of all, you realize I have to do parts on this one. You can't do this with just a normal u substitution. So we must choose the u is something and the dv is something. And basically, you look at the original integral, you identify two things being multiplied together. One of those things is going to be the u, the other of those things is going to be the dv. And just because I know how to do it, I'm going to choose u to be x and dv to be e to the x dx. So when you make your choices, you always include the dx as part of the dv, just in order for this all to work out. So dx always goes in the dv, all right? I made that choice. Now, I could have chosen it the other way around, but actually this is the correct choice to use in this example, and I'll talk more about that in a moment. Anyway, you choose the u and the dv. Now, if I intend to use the formula in the box there, this formula involves v and du. So those we must calculate. Du and also v. And just like in a u substitution, du is the derivative of u. So in this case, the derivative of x is 1. And also, just like in a u substitution, we always include dx as part of the du. All right? So the du in this case is just 1 dx. And the v, you never do this in a u substitution, but here, if you have u, the du is the derivative. Here, if you have dv, the v is the antiderivative of the dv. And so the v here is the antiderivative, which you can probably do in your head, but if I were to write it out in steps, it's the antiderivative of the dv. And what is the integral e to the x? It's e to the x. E to the x. Technically, it would be plus c, but because of the way the integration by parts works out, you don't have to write the plus c here. We're gonna account for that later on. So I'm never gonna write the plus c when I'm doing integration by parts like that. All right. So you choose the u and the dv. Based on that choice, you calculate the du and the v. And now it's just a matter of plugging into the integration by parts formula. So the parts formula says uv minus integral v du. I'm going to try and say that over and over again so that everybody will have it memorized. uv minus integral v du. It is x, that's u. V is e to the x minus integral v is e to the x. Du is dx, like so. All right, this is my integration by parts formula. Now, we're not done yet. There's still an integral that we have to do, but like I said, the hope is that the integral that you get here is easier to do than the one you started with, and that is the case in this example. Now we end up with just integral e to the x. Integral e to the x is e to the x plus c. So the last step is to actually do that integral there, and I just get e to the x. And here I'll put the plus c. This is why it's not really necessary to put the plus c in here. It would end up being in here anyway. All right. Like that. This is my answer. Any thoughts about that? Excellent. I was going to, can we, just like any integration, you can always check your answer when you're doing an antiderivative like this. You would check your answer by taking the derivative of what you end up at the end and making sure that it equals what you started with. So can we just try that once? I'm not going to do this every time, but you can always check the answer by doing the derivative of what I got in the answer. It's that, right? The plus c is going to go away immediately, so the plus c doesn't matter. But when I do this derivative, the first thing is x, e to the x. I have to do the product rule there. So it's going to be the first thing, x times the derivative of e to the x is e to the x, and then plus the second thing, e to the x, times the derivative of x, which is 1. And then I go minus, so that, all of this was the product rule from that, and then I go minus e to the x, but I take the derivative, it will again say minus e to the x. Then the plus c goes away. And what do you know? This e to the x times 1 will cancel this minus e to the x. You're subtracting the same thing. And so the whole thing is just x e to the x, which is indeed what I wanted it to be. The thing inside the integral. All right, so it worked. This is the integration by parts. Everybody's favorite first example. All right. So apart from just like plugging everything into the formula and making sure it works out, the thing to discuss is how did I know that you should have chosen the u to be the x and the dv to be e to the x? You could have chosen it the other way around. U equals e to the x, dv equals x dx. How do you know which one to choose? The reason I chose u equal x is because I knew ahead of time that when we eventually do this stuff, the thing inside of the integral here involves du, not u. And this, I chose this u so that the du would get simpler. And I chose this dv so that the v was, I mean, it's the same thing again, not much more complicated, which ensures that this integral I end up with here is easy to do because the u got simpler. So the general strategy here is, here's the strats, as the kids on Twitch say. The strats is choose u to be a part which gets simpler, or I'll say, or the same, when taking the derivative. That's why I chose x to be the u. That's because the derivative of x is 1, which is even like simpler than just x. All right. You choose u to be the part which gets simpler, or maybe stays the same when taking the derivative. And for the same reasons, you choose the dv to be something which gets simpler, or maybe stays the same when taking the antiderivative. So you choose the dv to be the part which gets, I'm writing the same thing again, but I'm going to say antiderivative. Gets simpler or maybe stays the same when taking the antiderivative. All right? So, for example, for the u, it's generally a good idea to choose a polynomial part. If there is a part which looks like a polynomial, like a power of x, or even a more complicated polynomial, choose that to be the u, because then the du will be, again, a polynomial, but of a lesser degree, so it will be a simpler polynomial, right? Also, sometimes for the u, like this is the classic good choice for the u. I will say polynomial, but I will say maybe sometimes a trig function, like sine or cosine. Those ones don't get simpler when you take the derivative, but at least it more or less stays the same, right? The sine becomes a cosine, the cosine becomes a sine. And hopefully the other part will get simpler. So sometimes sine, cosine is a good idea here. I will say for the same reason, sometimes e to the x is a good candidate here because, again, it doesn't get simpler when you take the derivative, but at least it stays more or less the same. And ln x is also a good candidate for the u because ln is a weird function, but when you take the derivative, you get 1 over x, which is typically easier to deal with. So these are generally good choices for the u's. And then for the dv's, this is a little less clear cut. I mean, there aren't a lot of functions which actually get simpler when you take the antiderivative, but sine and cosine and e to the x are generally good choices for this because they don't get more complicated, right? They just kind of stay like they are. I will say sometimes polynomial if you gotta. Polynomial sometimes. Because a polynomial can get a little more complicated when you take its antiderivative, but it's still going to be a polynomial. All right. These are general principles. Of course, just like in a u substitution, there are general principles about how you should choose the u, but sometimes you have to kind of improvise or do something slightly weird. So there are some examples like that. But this is the basic idea. Any thoughts about that? And let me just reiterate, dx always is part of the dv. right? When you make these choices, usually you don't have to think about the dx very much, but technically it should go with the dv. All right, let's just try some more examples. I got a few. I got some for you. How about this one? E to the x times 3x minus 2 dx. All right. I'm going to do parts here. There is no u substitution that will make this work. Based on the strats, anybody want to suggest? What should I pick for the u? 3x minus 2. I like that idea. And the dv? E to the x dx. Yes, and thank you for including the dx as part of the dv. Great. These are good choices, I think. Of course, to really know, you have to just kind of work it out and see what happens. From here, we calculate now the du. That's the derivative of u, which is 3 dx. If I were doing u substitution, I would rearrange this a little bit, divide by 3. Actually, that's never necessary in the integration by parts. And then v would be the integral of dv. So it would be the integral of e to the x dx, which is just e to the x. All right. By the way, this right here is why dx always needs to be part of the dv, so that you can do this integral. Like, in order to do an integral at all, you need a dx in there. So you better put it as part of the dv so that I can plug it inside this integral. Anyway, let's do it. I'm ready for the integration by parts formula. It is uv minus integral v du, which is, okay, u, put these parentheses here. That's the u. V is e to the x minus integral v e to the x du is 3 dx. All right? Not done yet, but I'm feeling pretty good about this. You should, at this point, sort of look at this integral and think to yourself, is this an easier integral to do than what I started with? And the answer is yes. We can factor the 3 out, and then it just says integral e to the x. So 3x minus 2 e to the x minus 3 integral e to the x dx. And then integral e to the x is just e to the x, and that'll do it. 3x minus 2 e to the x minus 3 e to the x. And I put the plus c at the end, as always. That's how we do it. Any questions about that one? This is pretty straightforward integration by parts example. Right? Okay. I got 2 more, and then I have some for you all to try. Let's try one with not at e to the x. How about 3x cosine x dx? All right. What do you think here? Somebody else want to say? What should I pick for the u? Yeah? 3x is a good idea. That's the polynomial part. And then the dv, I guess, has to be the other stuff, cosine x dx. All right. Now we calculate du is 3 dx, and v would be integral of cosine x dx, and that is sine x. All right. And so I do my parts formula. uv minus integral v du. It is 3x. V is sine x. And then minus integral v is sine x. Du is times 3 dx. Right. And I like the looks of this. I think, again, we can factor 3 out of the integral, and then it just looks like integral of sine, which is negative cosine. So I go 3x sine x, that's all done, minus, first factor the 3 out of the integral. I said. Factor 3 out of the integral, and now the integral of sine is negative cosine. 3x sine x. So I guess it's going to be now plus 3 cosine x. Because the integral of sine is negative cosine. I flipped the negative to a positive. That's that. Any thoughts about this? These that we've done so far, I would describe as very straightforward integration by parts examples. All right, let's try one that's a little weird. How about integral of ln x dx? I don't know if you ever wondered, This is something we've never talked about before, the integral of the natural log. We've talked about the derivative of ln x is 1 over x, and also the integral of 1 over x is ln x, but the integral of ln x is something that we have not discussed yet. And that's because, actually, I don't know of a way to do this other than using integration by parts. You have to use parts to do this integral. How are we going to do it? It's weird because I don't actually see two parts here. I just see, please, for the love of God, don't say I see ln is one part and x is the other part. No, that's a red flag in the club. The two parts have to be multiplied together. Then this is not ln times x. It's ln of x. That's a function inside of another function. All right, really, this is one thing all by itself. I suppose then my other part, anyone, you got an idea? Yeah, the other part is just going to have to be times 1. And you may feel like, is that actually going to work? I just imagine a times 1 here. Turns out it is going to work. This is a weird one. Usually you don't do that, but we're kind of desperate because there's only one thing inside the integral. You have to just invent the other part and it's going to be a 1. So which one should I put, the u or the dv? The ln has to be one or the other of these. And you should think to yourself, is the ln something I like to take the derivative of? In that case, I should put it in the u, and then the du would be the derivative of that. Or is the ln something that I like to take the integral of? Then I should put it here, and the v should be the integral of that. Any ideas? Should it be the u or the v? You want to show me the fingers? The u or the v? Is that way too ambiguous? It should be the u. This is a bad idea. It should be the u, because ln is something that I know how to do the derivative, right? If I take u equals ln x, then du will be 1 over x, right? If you put ln as the dv, then what's the v? It would be the integral of ln, but I don't know what that is. I mean, that's actually the whole point of this whole problem, is finding the integral of ln. So don't put the dv, don't put the ln in the other one, all right? I better put a dx here, sorry. That's part of the du, right? And then, anyway, this means dv must be 1 dx, and the integral of that will be the v, right? Integral of 1 dx, which is x. All right. Okay, let's see what happens then. So, my integration by part formula, uv minus integral v du. Plug everything in. The u is ln x, the v is x, and then minus integral v, that's x. Du is 1 over x. Neat. Dx. All right. Excellent. Now what? I have ln x times x. That is what it is. Don't make ln x squared there. If you like, you can write x ln x. That's the same thing. You can't simplify that at all. What do you want to do with these guys over here? X times 1 over x? How about this? Can I just do each of these? This is 1/2 x squared, and then this is ln x, right? That's the integral of 1 over x. Any thoughts about that? I wrote this in red because this is a red flag. Yeah.
You should just simplify, put it x over x, and then make that.
You should just simplify, yeah. Is that wrong what I did, or just needlessly complicated?
Needlessly complicated.
Anyone have a stronger, harsher, hot take?
It's wrong because you didn't use a product rule.
It's wrong because, yeah, it's not even a product rule. Like, if you have multiplication inside of an integral, you don't just do each thing separately, right?
You do by parts, yeah.
Yeah, I guess. I mean, when you see multiplication inside the integral, that's why we have integration by parts. Like, if you could just do this, then you should have stopped me at the beginning of class today and said, hey, we're not going to do any of that, right? This is the whole point of integration by parts, is you cannot just do that, all right? This is very, I know you don't have to care about my emotional journey, but this is very demoralizing when I see people do this. Like, you just did the parts, and now you're going to play me like that? Like, this, you shouldn't do this. That's why we have parts in the first place. Don't do that. It is not only extra complicated, it's straight up wrong. So here, like he said, we should just simplify first. X times 1 over x, they cancel, right? It's just 1 now, dx, right? The x and the 1 over x. you could write it as x over x, which cancels and gives you 1. Okay, and now I can do that integral. It's an easy integral. We get x ln x minus just x. That's the integral of 1. And I put the plus c at the end. All right, that's how we do. Any thoughts about that one? I got a few for you to try. That's a weird one because there was only, it looked like there was only one part there. Okay, a few for you. How about x ln x, x over e to the 4x, and x times square root x squared plus 1. I'll tell you ahead of time, one of these is kind of a trick question. I'll let you think about that. You may be concerned about the division here. You should be concerned. Integration by parts is only for multiplication. So I will leave this up to you, but you have to rewrite this into a multiplication before doing the parts. You cannot directly do parts on a quotient because it's based on the product rule. Lose interest here. You should.
No,
yeah, you can simplify first,
Okay.
kind of like I did here.
Oh, okay.
They don't totally cancel, but
Okay.
it's close. All right. Good. That's good so far. Yeah, you're doing the same thing. Simplify these guys.
Okay.
Yeah. Okay. Mhm. It's 1 over yeah, this is a rule. So,
I know that's what I'm trying this version.
Sorry, I said one of these was a trick question. It's not because I forgot to write the dx in the middle one. That's not why. I just forgot. Sorry about that. For the middle one, you may find it helpful if you remember this little tidbit. That's a good little formula to remember. That is usually in that example. Right here. That's exactly what you're about to need to know.
Yeah.
Perfect. Yeah. Just yeah, those are good choices. And then this should be 1, 4, -4. Because of that thing with the K.
Oh.
Okay here. I think you're -4. It should be 1 or -4. You want to choose the U to get simpler. So back to U plus X, what you do is just choices.
There's second ones. Said that one of those is kind of your question.
All right, let's talk about these. Some people are still struggling with the last one. That's because the last one is kind of a trick question. But the other two are totally normal. So let's try the other two. And I mean, we'll do the last one also. But so let's do this first. X times ln x. For this one, you should choose u to be ln x and dv to be x. Then the du is 1 over x dx. And the v is the integral of x, which is 1/2 x squared. Right? As I was walking around, people, for the most part, worked this one out. uv minus integral v du looks like ln x times v is 1/2 x squared minus integral v is 1/2 x squared times du is 1 over x dx. And then we are going to, this looks complicated, but actually it can simplify. I have x squared times a 1 over x. They will cancel the x's, and it's just x is left over. And I'm also going to pull the 1/2 outside of the integral. So this looks like ln x times 1/2 x squared minus. Okay, factor the 1/2 out, and then all that's left on the inside is just x. And then the integral of x is 1/2 x squared. So this will be pretty much it. Ln x 1/2 x squared minus 1/2. And then times, again, another 1/2 x squared. Like that. This is what I got. You can make 1/4 there if you want. Any questions about that one? I hope that, I mean, pretty much folks seemed to get that one okay. Okay, the next one, which had the e part. This one is slightly weird in that it looks like a quotient. Like I said, you must rewrite this like a product because the integration by parts is not meant to be used on a quotient because it's based on the product rule rather than the quotient rule. So first, before doing anything, you should rewrite it like that as a product. And now I'm going to choose my parts. And as usual, I have a x part, like a polynomial part, and a e part. I'm going to use u equal x here. That's because when I do the du, it goes away entirely. It just becomes 1 dx. And then the other part has to be e to the minus 4x dx. And then the v will be the integral of that. And by this business with the like this, this is a handy dandy formula to remember. Integral e to the kx is 1 over k e to the kx. That's what I'm going to do in this step right here, where k is -4, so it will be 1 over -4 e to the -4x. That's my v. All right. And then do your business. It is uv minus integral v du. And the answer is u is x, v is 1 over -4 e to the -4x. Okay, that's uv minus integral v du. V is 1 over -4 e to the -4x. And then du is 1 dx, like that. How am I doing? All right. Okay, and now to finish, I would factor this constant out of this integral and then integrate e to the 4x again, e to the minus 4x again. So x times, just about done here. And then minus, I'm going to pull this constant out. This constant is negative already, so I'll make it a plus. E to the integral e to the minus 4x dx. And what is that? It is another 1 over -4 e to the minus 4x. So it's like this. That's my final answer. Any thoughts about that one? I hope you got that or something like it. All right, great. And the last one, which I said was a bit of a trick question. It is a trick. On the surface, it looks kind of like you might want to use integration by parts because I do indeed see a multiplication right there. But I think some of you saw through my deception. What should you actually do in this one? Yeah, you should do a u substitution here. You can try in vain to choose the parts one way or the other way. You will see complications either way, basically from this part, right? If you let this be the v, taking the dv involves doing the chain rule and it gets more complicated. Or if you let this be the dv, you have to integrate it and that's not even possible to do. So parts is just not going to work here. This is a a u substitution one. All right, I'm not sure we need to go through the details, but the moral of the story is when you see multiplication on the inside of the integral, that doesn't always mean that you should do parts. It sometimes means you should do the u substitution, and it's up to you to decide. For a given integral, you kind of have to decide for yourself which of your various tricks to use on it, right? So far, we only have really two tricks, the u substitution and the parts. But as we go on, we're going to talk about yet some more tricks. And it can be a bit of a challenge to decide which to use. Although, a little pro tip for the sake of our class and the quizzes and the tests, if it's problem number 10, which is the integration by parts problem, it's a little pro tip. You should probably use the integration by parts on that. So because of the way our tests work in this class, you actually won't have to think too much about which method am I supposed to be using here, because I'm going to tell you for the most part. All right, excellent. We got 10 more minutes. One more thing to say. Two more things that I think we can say in 10 minutes. I have two more examples. I wanted to have you guys try another. Maybe we'll try that at the beginning next time. So, two more interesting things that can happen. Let's just look at one here. How about this? 7x squared e to the x. All right? This is innocent looking, and it's not all that hard, although you'll see something slightly weird happen. So I'm going to do my parts. Let's just pretend like nothing's weird about this. I'm going to choose a polynomial part and an exponential part. And the polynomial part is that first part, and I'm going to make that the u, just because I know that you should usually choose the polynomial to be the u, because the du then will be simpler. It's 14x. All right? And then the other part, dv, is apparently e to the x dx. And so v is the integral of that, which is, again, e to the x. Sorry, my du should have dx in it. All right. These are my parts. Plug into the parts formula. uv minus integral v du. If I say it enough times, maybe we'll all remember it. The u is 7x squared times the v is e to the x, and then minus the integral. V is e to the x. The du is 14x dx. All right. Now, at this point, we have to do this integral here. I would like to, like if you look in our previous example, sometimes we simplified. This, we could, I suppose, factor the 14 out, although it doesn't really simplify much more than that, but I'll do that at least. 7x squared e to the x minus 14 integral, and just because I like it better, I will write the x first. X e to the x. I like the looks of that better than e to the x times x. That doesn't really matter though. All right, and how do we handle x times e to the x? This is a little thing that never happened in our previous examples. Anyone got an idea? You gotta do it again, she says. Yes, do the parts again. Sometimes you do the parts again. That's how it works. And it's maybe not such a surprise because you can, if you think about it this way, we started with a quadratic. After I did the parts, the effect of that was to reduce it now to a degree 1 polynomial. And if I do the parts again, it should reduce it again to make the polynomial disappear entirely. Generally speaking, if you had, say, a polynomial of degree n, you should expect to do the parts n times to make the polynomial go away. All right, so let's do the parts again. I make a new choice of a u and a dv. The u is, I'm going to choose x, because that's how I do it when part of it is a polynomial. Then the du is 1 dx, and the dv will be the other part, e to the x dx, and the v will be the integral of that, which is e to the x. All right? So I got 7x squared e to the x minus 14. And now put parentheses here. The 14 has to distribute across what I'm about to write. And it's going to be, again, uv minus integral v du, where I'm talking about the new u's and v's here. So I go uv, that's x, e to the x, minus integral v du, that's e to the x dx. All right? We're still not done because there's still an integral to do, but now this integral is very easy. Integral e to the x is e to the x, and that'll do it. So this is my final answer, 7x squared e to the x minus 14 x e to the x minus e to the x. And then I put a plus c all the way at the end. This is how we do it. Right? Any thoughts about that one? That is, sometimes you got to do the parts more than once. There are some truly absurd examples. We're not really going to do this, but there are some examples where it's like you do the u substitution to transform the integral, and then you do parts to that. Or you could sometimes do parts once and then do a u substitution. Or you could do like parts twice and then a u substitution and then parts 3 more times. Like it is possible for these kind of combinations of these various techniques, although I'm not into that. We're never going to do examples like that. One last thing to say, we got 4 minutes remaining, and this is just real quick. What about definite integrals? This is something, I don't know if you noticed. Definite integral. Definite integral is the one with the little numbers. This is not hard to do, although we do need to say, just to say, like, what are you even supposed to do with little numbers if you're doing the integration by parts? I think we can just do an example, and we'll all see what to do with the numbers. We should just do one so that we see how it's done. The basic idea here is ignore the numbers, ignore the boundary values, do the parts as usual, and then plug them in at the very end. Plug them in everywhere. You'll see what I mean by everywhere at the end. All right. So let's try this one without just disregard the 1 and the 3 for now, and we'll take care of them at the end. And I want to suggest that is a quotient. We need to write it as a product instead. How should I rewrite that? I don't like the fraction there. Yeah? Yeah, great. I like that. Okay, so this is how we're going to start to do it. Now there I'm going to do parts. My choices are x to the minus 2 and ln x. I'm going to choose u equals ln x. If you see a log in there, you basically have to put that as the u, because the integral of ln x is nothing, or it's a weird, complicated thing, and I'm not into that. Du then will be 1 over x dx. And then the v is the other part, x to the minus 2. Sorry, that's dv, x to the minus 2 dx. And so v is the integral x to the minus 2 dx. We increase the power by 1, it becomes x to the minus 1, and then divide in front by that, it's minus x to the minus 1. All right, that's the v. Okay, all right. Do my parts here. uv minus integral v du. That is, u is ln x, v is negative x to the minus 1 minus integral v negative x to the minus 1 times du 1 over x dx. All right. Sorry, I know it's time to go. We're almost done here. Let's simplify inside the integral. What does this look like when you simplify? I'll pull the minus sign out and make everything a plus. I'm good for that part. What do we get inside the integral when we simplify? Yeah. X to the negative 2. Yeah, both of these guys are actually 1 over x. It's probably better to think of them both as x to the minus 1, and you combine them to get x to the minus 2. Great. And that's an easy integral to do. Minus x to the minus 1 plus... Okay, the negative 2 increases to a negative 1. It ends up being minus x to the minus 1. All right. Look at that. I was about to write plus c. Don't write the plus c, though, because I had the little numbers at the beginning. What do? You wait till the very end, and then I said, plug the numbers. What I said here? Plug the numbers in everywhere at the end. What I mean by that is, like, this integral here gave me only that last bit, but you really do have to plug these numbers into the whole thing. So not only to this guy, to the whole thing here. Remember, the entire answer, if I'm doing a definite integral, the answer should be a number. It should not have any more x's in it. So you really need to plug those numbers in to every x that you see here. So it's going to be ln 3, negative 3 to the minus 1, minus 3 to the minus 1. That was the 3 I plugged in. Subtract. put some big parentheses, and now the rest of it. ln1, negative 1 to the minus 1, minus 1 to the minus 1. Like that. All right, that'll do. Thank you for your attention.